Hello, my name is Valerie Stolf, and this is my Physics 2211 video report for Lab 3. In previous labs, we used fundamental principles and known forces to predict the future motion of some object. In this lab, we are exploring how we can use an observed trajectory and fundamental principles to work backwards and find the net forces acting on a star. A star of mass 2 times 10 to the 30th kilograms is orbiting a black hole of unknown mass. From the object's trajectory, the objective was to calculate the net force, which is assumed to be only that of gravity from the black hole, at every location to ultimately estimate the mass of the black hole. Overall, I used the universal law of gravitation and rearranged it to find the mass of the black hole, which was estimated to be 1.20725 times 10 to the 35th kilograms. The main physics principles applied were the relationships to momentum and net force, where the change in momentum is equal to the net force times the change in time, and the relationship between momentum and velocity, where momentum is just the mass of the object times its velocity. Furthermore, Newton's universal law of gravitation was used to relate the two objects at play using the distance between them and each of their masses. From here, understanding of force components was used to separate the net force and momentum into each of their components. The parallel component is responsible for the speeding up or slowing down of the object, and the perpendicular component is responsible for the object changing directions. Together, the two components add together to give the overall net force. The calculations are shown on this slide. GlowScript was used to generate the star's path and determine the black hole's mass. From the starter code given, I edited the mass of the star and the change in time to reflect 1 year of time. From there, the x and y components of the star's position were edited to reflect how the principles would change between locations. In the second image, the principles discussed in the previous slide were used to compute the momentum and net force in each of their components to allow for the change in position to show the change in net force at each location. In the third image, on lines 180 to 184, I edited the code to directly compute the mass of the black hole and print it. After some trial and error in adjusting the aeroscale, I settled on a very small value that would reflect the relative force magnitudes in each location. This value is 1 times 10 to the negative 18th. When the code is run, it is evident that there is a significant amount of force that occurs when the star is near the black hole, and the arrows are not visible once the star gets further away from the black hole. This is because the force of gravity is considerably less because the distance is much larger. Here, the component forces are also depicted when the star is near the black hole. I'll show it again. The black arrow which will be shown is the parallel component, which is shown to be parallel to the object's motion. The red arrow is the perpendicular, which points toward the center of the kissing circle. The overall force arrow is in yellow, which is in between the other two, and always pointing towards the black hole. To conclude, I will discuss the questions presented in this assignment instructions. First, the net force and its components are different from the time rate of change momentum and its components because the time rate of change momentum is a result of the data observation, and the net force is computed from the results from the GlowScript trajectory. The parallel component will only change if there is a change in the magnitude of the momentum, but the perpendicular component will only change if there is a change in the magnitude of the object's direction of motion. For the second question, we were asked to analyze a potential difference in the calculated mass of the black hole if it were to be replaced by an entirely different black hole. In this scenario, it is assumed that the gravitational force is the only force acting on the star. The star is the same as before, with the same mass, the path of motion is still the same. Because of this, the distance squared is still the same at every point. And in order for the trajectory to be the same, momentum and velocity must also be unchanged. So, according to the universal law of gravitation, the gravitational force has to be the same as well. This means that a different value for the mass of the black hole cannot be found because the trajectory is still the same. Thank you for watching.